Hello my friends, and welcome back to the You Can Do TV channel. Constructed between 1887 and 1889, the Eiffel Tower used puddled iron, an early form of structural steel, manufactured by the Pétain et Godey foundry. Over 7,300 metric tons of this wrought iron were assembled into 18,038 individual parts. Precision drilling replaced on-site cutting, and components were riveted together using 2.5 million hand-driven rivets. The tower's lattice structure ensured high strength while minimizing wind resistance. Inside this advanced steel mill, precision meets power. Heated billets enter the descaling unit, removing surface impurities. Rough rolling forms the initial shape, followed by finishing stands that define the final H-beam profile. Ultra-fast cooling enhances strength before beams are transferred to the cooling bed. A powerful straightener corrects deformations, and cold saws cut beams to exact lengths. Finally, beams are bundled, weighed, and dispatched, ready to support the world's most demanding structures. The post-processing of seamless steel pipes involves a series of meticulous technical procedures to ensure internal cleanliness, dimensional accuracy, and mechanical performance. First, operators manually insert probes into the pipe ends, checking axial continuity to confirm there are no obstructions like shavings or oxide scales. Any burrs or diameter reductions are removed to guarantee internal flow. The pipe then undergoes straightening via multi-roll or pressure correction systems to achieve precise geometry within tolerance limits. Fixed-length cutting follows, using sawing or plasma machines to ensure clean, burr-free ends. Next, the pipes are heat-treated, typically by annealing or normalizing, under controlled temperature and time settings, to relieve internal stress and refine structure. Finally, acid pickling is applied, immersing the pipes in a chemical solution to remove residual scale, rust, and impurities. This results in smooth, clean surfaces that meet industry specifications, completing the critical final stage of seamless steel pipe production. In the hot rolling process, steel is heated to extremely high temperatures, typically above 1,000 degrees Celsius, making it malleable and easy to shape. A series of heavy rollers compress and elongate the material into desired profiles such as sheets, bars, beams, or rails. Hot-rolled steel is widely used in construction, automotive manufacturing, and applications requiring high strength and durability. Its surface is generally rough, and dimensions are less precise compared to cold-rolled steel, but it excels in load-bearing performance. In a fully automated rebar processing facility, speed and precision drive every stage of production. From cutting to bundling, each movement is orchestrated for maximum efficiency. After precise cutting by the flying shear machine, the threaded steel bars are smoothly transferred to the bundling station via an automated roller or chain conveyor. Guided by photoelectric sensors and PLC control, Each batch is aligned and stacked according to preset specifications, typically 2 or 3 tons per bundle. At the station, the automatic binding machine engages. Using hydraulic or pneumatic tensioning, it tightly secures the bars with high-strength steel wire or polyester straps. The binding is completed with hot melt welding or mechanical buckling to ensure structural stability. Once bundling is finished, the electromagnetic suction crane activates. A powerful magnetic field is generated, lifting the finished bundle effortlessly from the line and transferring it to the designated storage area or loading point. The entire operation, fast, accurate, and efficient, demonstrates the precision and automation of modern steel bar processing. Beneath the roar of molten metal and the rhythm of industrial precision, a remarkable transformation unfolds, where raw materials are forged into the building blocks of modern civilization. This is the world of advanced steelmaking, where cutting-edge engineering meets relentless power. Altos Hornos de Mexico, AHMSA, operates as a fully integrated steel producer, transforming raw materials, iron ore and coal, sourced from its own mines into high-quality steel products. Steelmaking starts by the treatment of iron ore through pelletizing and sintering, while coal undergoes coking. Iron ore slurry is pumped through a 300 km pipeline to the pellet plant, where it's filtered, mixed with binders, shaped into pellets, and hardened at 1,300 degrees Celsius. Simultaneously, metallurgical coal is carbonized in refractory-lined coke ovens for 18 hours, producing coke essential for blast furnace operations. The sinter plant utilizes iron-bearing materials like fines, mill scale, and fluxes to form a porous mass, which is hardened in a continuous sintering machine and sent to the blast furnace along with coke and fluxes. Inside the towering blast furnace, at temperatures reaching 1,650 degrees Celsius, iron oxides are reduced, yielding hot metal. The molten metal is tapped into ladles and transferred to the desulfurization station, where impurities are removed using calcium carbide and magnesium. Steelmaking occurs via basic oxygen furnaces, BOF, or electric arc furnaces, EAF, where hot metal and scrap are refined with oxygen, argon, and nitrogen injections. Secondary metallurgy includes ladle refining, vacuum degassing, and alloying for precise chemical composition. Liquid steel is cast into slabs via continuous casting, then hot-rolled into coil or plate. Reheating to 1,300 degrees Celsius, slabs pass through reversing or Steckel mills, then cooled and coiled. For higher strength and surface quality, the coils may undergo cold rolling, acid pickling, annealing, and temper rolling. AHMSA also manufactures structural steel, tinplate, and chrome-coated sheets for construction and packaging industries. Supporting infrastructure includes in-house power generation, gas production, oxygen, nitrogen, carbon dioxide, and advanced water treatment. AHMSA's vertically integrated system adheres to strict international standards for quality, safety, and sustainability, delivering steel with precision and technical excellence. Primetal's Technologies Bloom casting systems deliver high-performance metallurgical control through advanced automation and design. Featuring straight molds for uniform primary solidification, Dynaflex hydraulic oscillators, and Levcon mold level control, these casters ensure dimensional precision and steel cleanliness. Technologies like Dynagap 3D enable dynamic soft reduction, while SRD and DryStar spiral rollers optimize strand guidance under high thermal loads. CVS Technologies delivers a fully integrated mini-mill in Oran City, Algeria, with 1.25 million tons annual liquid steel capacity and 800,000 tons rebar output. The facility features a 120-ton electric arc furnace, a ladle furnace, and a 6-strand high-speed caster producing 1.5 million tons of billets yearly. A 130-ton per hour walking beam reheating furnace enables both hot and cold charging. The rolling mill achieves 13 meters per second finishing speed and produces rebars from 8 to 32 millimeters diameter. Weldable high-tensile bars are formed via an advanced quenching system. Full process automation ensures production efficiency. The plant recycles water and uses a fume treatment system, aligning with environmental standards while reducing Algeria's steel import dependency. At FESCON 2023, the Continuous Preheating System for Electric Arc Furnace (EAF) operations drew significant attention for its energy efficiency and performance enhancement. This system utilizes recovered off-gas heat to preheat scrap metal up to 600 degrees Celsius before charging, significantly reducing tap-to-tap times and lowering electrical energy consumption per ton. Its shaft-type design allows uninterrupted scrap feeding, while Smart Flow Control maintains optimal temperature distribution. Integrated with real-time monitoring and automation, the system ensures precise process stability and reduced electrode wear. Benefits include up to 25% energy savings, improved furnace productivity, and minimized carbon emissions, making it ideal for modern steel plants targeting both cost efficiency and environmental sustainability in continuous EAF production cycles. A 50 cubic meters blast furnace, operated by Shanghai Metallurgy Group, is shown in action. The process begins with raw material feeding through the top. Inside the furnace body, iron ore, coke, and flux are smelted under high temperatures. The hot blast system injects preheated air to intensify combustion. Molten iron is released through the iron tapping hole, while impurities are removed via the slag tapping hole. The iron is then cast, and slag is safely discharged. In a blast furnace, iron ore, coke, and limestone are heated to around 2,200 degrees Celsius. The coke provides carbon for reduction, producing molten iron. Impurities form slag, which is removed. The resulting hot metal is rich in carbon and other elements, requiring further refinement to create usable steel. The seamless pipe production line by Shanghai Metallurgy Group showcases high-precision engineering and advanced automation. A solid round billet is heated and pierced by a diagonal rolling system, initiating the formation of the hollow tube. The process ensures rapid deformation with controlled accuracy. Following piercing, the billet passes through continuous or three-roll cross-rolling mills, then enters the sizing and reducing machines to achieve final dimensions. Straightening systems correct any distortion, and hydrostatic pressure testing confirms pipe integrity. The entire line includes automatic piercing machines, tube rolling mills, and reeling systems, engineered for high-efficiency production of carbon and low-alloy seamless steel pipes with superior structural. On the modern rail production line, the straightening and finishing unit features fully automated machinery working in perfect coordination. Powerful hydraulic straighteners correct any deformation, ensuring precise geometry. High-speed inspection systems scan for surface and internal flaws. Robotic grinders refine the rail surface, while automatic marking units apply identification codes. Final alignment and dimensional checks guarantee consistency before bundling, delivering rails that meet the highest standards of accuracy, durability, and performance for global infrastructure. PPRM has commissioned a high-speed TMT rebar mill for Wataniya Steel in Riyadh, engineered for precision and high productivity. Operating at 30 meters per second for 10 mm bars, the mill handles rebar sizes from 10 mm to 40 mm, with an annual capacity of 600,000 tons. The system includes rapid quenching lines, automatic loop control, and advanced HMI-based automation. It achieved 1,750 tons per day and 995 tons in a single shift during performance trials. Designed for thermal and dimensional consistency, the installation highlights advanced rolling technology, minimal downtime, and high mechanical reliability under continuous operation, delivering top-tier metallurgical performance. At Huigang Special Steel, the EAF Quantum system integrates advanced engineering for efficient steelmaking. Featuring fully automated scrap loading and a shaft preheating design reaching 600 degrees Celsius, it reduces energy use and electrode wear. The fast tapping system enables underpower steel tapping, minimizing delays. Intelligent control, dynamic exhaust paths, and forced air slag treatment optimize emissions, noise, and cycle time, achieving 32-minute tap-to-tap performance with 230 kWh/T energy consumption and up to 30% lower electrode usage. Witness the intensity of iron making as molten iron is tapped from the blast furnace in a precisely timed operation. Using high-temperature resistant refractories and automated clay gun systems, the tap hole is opened to release liquid iron into torpedo ladles. Every phase, from furnace pressure control to slag separation, is engineered for maximum efficiency, safety, and flow continuity. This dramatic process fuels steelmaking worldwide, powering industries with a constant supply of high-purity hot metal. The smooth long product, rebar production line at Shanghai Metallurgy Group integrates advanced automation and metallurgical precision. Billets are uniformly heated in high-efficiency furnaces, reaching 1100 to 1250 degrees Celsius to ensure proper plasticity. They then enter a multi-stand continuous rolling mill, where controlled deformation shapes them into precise diameters with embedded ribs. Following rolling, thermomechanical treatment applies rapid quenching to form a tough martensitic surface while retaining a ductile core. Shearing units cut rebars to length before controlled cooling on beds. Each product undergoes strict quality inspection for strength, accuracy, and surface integrity. The fully automated system guarantees consistent output, energy efficiency, and premium construction-grade performance. Steel slab production using a continuous casting machine, Concaster, ensures high precision and flexibility. Slabs typically range from 800 to 2,500 mm wide, 150 to 400 mm thick, and 4 to 12 meters long. The system accommodates various steel grades, from carbon and low alloy steels to stainless and specialty steels. Advanced automation, electromagnetic stirring, and optimized cooling guarantee superior surface and internal quality for downstream applications. The process begins with heating brass billets to 800 degrees Celsius. These billets are then forged into shape using high-pressure molds. Subsequent CNC machining ensures precise dimensions. The fittings undergo polishing for a smooth finish, followed by surface treatments like electroplating. Finally, each piece is inspected for quality assurance. The automatic LPG valve assembly machine efficiently assembles components with high precision. First, parts such as valve bodies and springs are fed into the machine through vibrating feeders. Robotic arms and pneumatic systems accurately position each part. The assembly process involves inserting springs, valve pins, seals, and tightening caps. Sensors monitor each step to ensure proper assembly and detect faulty units. Completed valves are automatically transferred to the inspection area. The machine operates continuously and reduces labor, ensuring consistent quality and increased productivity in LPG valve manufacturing. The precise production of a brass fitting bracket. The process includes cutting brass rods, CNC machining, deburring, polishing, and threading. Each step ensures high-quality parts with accurate dimensions and a smooth, shiny finish. The brass valve production industry plays a critical role in plumbing, HVAC, and industrial applications, with global demand surpassing 1.2 billion units annually. Brass valves are favored for their corrosion resistance, machinability, and durability. Typically made from alloys containing 60 to 70% copper and 30 to 40% zinc, these valves are manufactured through forging or casting processes. In 2023, the global brass valve market was valued at approximately $3.8 billion United States dollars, with projections indicating a CAGR of 4.5% through 2030. Major production hubs include China, which accounts for over 40% of global output, followed by India, Germany, and the United States. Production begins with hot forging, where billets are heated to around 750 to 850 degrees Celsius and formed under 300 to 800 ton presses. After trimming and shot blasting, precision CNC machining ensures tolerances within plus or minus 0.01 millimeters. Surface finishing and chrome or nickel plating enhance appearance and durability. Each valve undergoes pressure testing at 1.5 to 2 times the rated working pressure, often 16 to 25 bars. Automation has improved throughput, with modern plants producing up to 10,000 valves per day. As water conservation and sustainable materials become priorities, innovations in lead-free brass and smart valve integration are driving next-generation development. At Hepiral, the production of brass bells begins with flat brass sheets. These sheets are first precisely cut to size. They are then heated to make the metal more malleable and easier to work with. Once softened, the sheets are carefully hand-hammered into a rough bell shape. The next stage is spinning. This process involves rotating the metal on a lathe while shaping it with tools to form the final bell contour. Skilled artisans continue to refine the bell's shape with additional hammering. Following the formation of the bell, other key parts of the instrument, including the lead pipe and valve section, are assembled. Each component is aligned and soldered by hand to ensure accuracy. Special attention is given to the valves, which must move smoothly and seal perfectly. Brass tubing is shaped using mandrels and filled with a stabilizing material during bending to prevent deformation or wrinkling. Once the instrument is fully assembled, it undergoes polishing and cleaning. Finally, it receives a durable, high-gloss lacquer or a silver-plated finish to protect the surface and enhance its appearance. First, the craftsman selects and prepares pure copper sheets, ensuring they have the proper thickness for durability and heat conduction. Next, the sheet is cut into a circular shape that matches the desired pan size. Then, using a hammer, the craftsman begins forming the basic bowl shape. This hammering process not only shapes the copper but also strengthens it, laying the foundation for the final form of the pan. Copper sheets are first cut and shaped into decorative panels. These panels are then carefully bent and soldered together to form the lantern's frame. Holes are drilled for assembly, and edges are smoothed. Afterward, the lantern is cleaned and polished for a refined look. Glass panes are inserted into the frame, and metal components are riveted or screwed in place. The finished copper lantern is both functional and ornamental. At SPV, valve production begins with precision investment casting using automated wax injection and robotic dipping. Ceramic molds are dried in conveyor systems before metal is melted in induction furnaces and poured. Post-casting, components undergo CNC machining, heat treatment, and polishing. Final assembly includes rigorous testing to ensure quality and performance. This process guarantees high-quality valves for various industries. At the horn foundry, recycled metals are sorted, melted in high-temperature furnaces, and cast into new components, ensuring material purity and quality. At the CCR refinery, spent catalysts undergo continuous regeneration. They are oxidized to remove carbon deposits, reduced to restore activity, and reintroduced into the process, maintaining efficiency and minimizing waste. The production of copper vase parts begins with metal discs being placed on a spinning lathe. Using a forming tool, a skilled operator shapes the rotating copper disc over a mold to create the desired profile. This metal spinning process is done manually, requiring precision and control. After forming, excess material is trimmed, and the part is removed. The surface may be further refined by sanding or polishing. Each piece is carefully crafted, resulting in a smooth and symmetrical copper component. This traditional process highlights the craftsmanship involved in transforming flat copper sheets into elegant vase parts. To create an enamel copper bowl, a copper disc is clamped against a wooden form on a lathe. As the lathe spins, a steel tool shapes the copper over the mold. Wax is applied to reduce friction, and the rim is smoothed with a chisel and filed. The finished copper bowl is cleaned thoroughly to remove wax. A glucose-based clear fire mixture is applied, followed by a layer of fine enamel glass. The bowl is gently placed on a trivet and fired in a kiln, bonding the enamel to the copper for a smooth, colorful finish. The HVGIS termination installation begins with unpacking the kit and checking all components against the list to ensure completeness and compliance with field quality standards. Installers must thoroughly study the installation drawing and instructions before proceeding. The cable sheath is measured and stripped, exposing the brass tape under the lead sheath. An extra cable length is left for adjustments. The brass tape should be wrapped around the lead sheath for at least 60 millimeters. Copper wires are cut, leaving 500 millimeters, bent backward and temporarily fixed. Aluminum foil is applied over the Dover-wrapped cable, followed by uniform heat application. Heat shrink tape is fixed with PVC tape, and a second aluminum foil layer is added. The cable is kept at 80 degrees Celsius for 3 hours, then cooled naturally for at least 8 hours. Once cooled, the swelling water tape is removed. An excess cable is trimmed. The semiconductive screen and insulation are stripped and polished according to the installation drawing. Brass tape is fixed to the sheath, and electrical layers such as water block tape, copper mesh, and PVC tape are applied. Finally, all components are installed in the proper sequence. The installation begins by stripping the outer sheath of the armored or screened copper cable. After removing filler materials, the cable screen is folded back. The inner insulation is then stripped to expose the conductors. A heat shrink tube is slid over the cable. Conductors are inserted into the mono heat shrinkable joint and crimped. A sealing mastic is applied over the crimp area, then the tube is centered and heated evenly, using a torch until fully shrunk. The joint is allowed to cool, forming a sealed, insulated connection, suitable for outdoor or underground use. At U.S. Tsubaki's whole yoke plant, roller chains are expertly crafted through precision machining, heat treatment, and rigorous quality checks. Advanced automation ensures each component meets exacting standards, resulting in durable, high-performance chains that power industries worldwide. The UBC recycling machine processes aluminum cans through shredding, paint removal, melting, and purification. Aluminum wheels are fed into a hammer mill, where rotating hammers crush them into smaller fragments. These fragments are then separated by a magnetic separator, removing ferrous metals. The remaining non-ferrous aluminum pieces are collected. The aluminum rotor recycling process involves a hammer mill that crushes rotors into smaller pieces. These fragments are then passed through a magnetic separator, which extracts ferrous materials. The remaining non-ferrous metals, primarily aluminum, are collected for further recycling. This efficient method ensures effective separation and maximizes material recovery. The Revax D16 wire bending machine operates by manually feeding a rod into the machine. Once inserted, the machine's CN-controlled bending head executes precise bends according to program specifications. The process involves sequential bending operations to form the desired shape. After completing the bends, the machine releases the finished piece, ready for collection. This semi-automated process ensures accuracy and efficiency in wire shaping tasks. The multifunction threading and chamfering head integrates threading, chamfering, and bending into a single CNC-controlled process. It efficiently produces complex wire forms and springs with high precision, enhancing productivity in various industries. This company specializes in producing durable, precision-engineered aluminum products, including versatile profiles for industry, high-performance doors and curtain walls for buildings, and hygienic, eco-friendly packaging solutions for food, pharmaceutical, and cosmetic applications. The FAMAC milling machine precisely removes material from a metal workpiece using a rotating cutting tool, shaping it into the desired form. The Aerospace heavy-duty lathe rotates large metal parts while a stationary cutting tool shapes them, ensuring high precision in turning operations. The process begins with a flat, circular aluminum blank, 2 mm thick, mounted onto a spinning lathe. A mandrel defines the final shape, and the operator uses scissor tools to press the blank against the mandrel as it rotates. These tools reduce physical effort due to the pivot mechanism, making the process less labor-intensive. Through controlled force, the aluminum conforms to the desired shape, meeting precise dimensional requirements. Once formed, the component is deburred to remove sharp edges. After additional fabrication and quality inspection, the base is ready for use in the electrical hub assembly. The Multis U4000 performs a spiral finishing process with high precision, integrating turning and milling in a single setup. The machine utilizes synchronized motion and advanced control to achieve a smooth, continuous spiral surface, reducing setup time and ensuring superior surface quality on complex parts. The machining process on the Okuma Multis B250 begins with loading the workpiece onto the main spindle. Next, turning is performed to shape the outer diameter. Then, milling operations create flat surfaces and slots. After that, drilling is carried out precisely. Subsequently, tools are automatically changed. Finally, finishing operations are completed and the workpiece is unloaded. Witness the raw power of steelmaking as tons of scrap steel are transformed into massive ingots. Preheated in the charging bin for optimal efficiency, the scrap is smelted at temperatures nearing 1,800 degrees Celsius. The molten metal roars to life, releasing impurities through slag discharge. Transported in ladles, the steel undergoes refining to remove gases and inclusions. Once poured and solidified, the glowing ingots emerge, ready for forging, rolling, or machining in heavy industrial applications. This is the essence of large-scale steel production in modern Chinese foundries. The 500mm large HBAM production line showcases high-precision metallurgy and intelligent manufacturing. From billet heating to final rolling, advanced temperature control and micrometer-level shaping ensure structural accuracy. Smart systems monitor real-time performance, ensuring efficiency and product quality throughout this cornerstone of modern steel production. The Bar Hot Rolling Mill, designed by SINOM Group Company, Limited integrates advanced metallurgy and automation technologies to deliver efficient and high-quality production. Featuring hot billet charging, rotary flying shears, and high-rigidity short-stress path rolling mills, the line ensures precise deformation control and mechanical strength. The vertical sectional combined reducer optimizes torque transmission, while water cooling and a walking beam cooling bed improve metallurgical properties and surface quality. A fully automated bar counting, separation, and bundling system streamlines post-processing. Notably, SINOM's multi-strand slit rolling technology enables one billet to be longitudinally divided into 2 to 4 strands using specialized roll passes and guiding systems. These strands are simultaneously rolled to final size and cut at high speeds, up to 20 meters per second for dual strands and 15 meters per second for triple or quadruple strands, before being transferred to the cooling bed. The result is a cost-efficient, high-output line tailored for both construction and alloy steel applications. The production of steel bars begins with heating solid steel billets in a high-temperature reheating furnace, reaching approximately 1,200 degrees Celsius. Once the billets are sufficiently softened, they are passed through a series of automated rolling stands. These rolling mills gradually reduce the billet size and shape them into long steel bars with precise dimensions. After hot rolling, the bars are cut into specific lengths and further processed into wire rods, depending on the final product requirements. The steel coil are then transferred to a cooling bed, where they undergo natural air cooling. This controlled cooling process is crucial for refining the microstructure and enhancing the mechanical properties of the steel. Following cooling, the steel bars are automatically gathered into bundles or tightly wound into coils using mechanical binding systems. This step ensures easy handling, storage, and transport. Each coil or bundle is then labeled, weighed, and inspected for quality before being moved to dispatch areas. Automated crane systems or conveyors transport the finished bars to storage facilities or directly to loading docks for shipment. This streamlined, high-efficiency process ensures consistent quality and timely delivery of steel bars for construction, infrastructure, and industrial applications. How do structural steel autostacking machines operate? Structural steel autostacking machines by Shanghai Metallurgy Group integrate 3D scanning, robotic arms, and smart gripping systems to boost efficiency up to 5-fold. With 99.5% precision and reduced defect rates, they enhance safety and sustainability. Modular, 5G connected design supports smart manufacturing goals under China's Industry 4.0 strategy. At Finkel Steel's Sorel Forge in Quebec, Canada, giant steel blocks are crafted through a rigorous, multi-stage process tailored for aerospace-grade applications. Production starts with the melting of premium alloy steel in an electric arc furnace. Carefully selected scrap and alloying elements such as nickel and chromium are combined and refined in a ladle furnace to achieve precise chemical properties and remove impurities. Once molten, the steel is poured into large ingot molds and allowed to solidify. These ingots are then reheated in massive forging furnaces to optimal temperatures for hot working. Using powerful hydraulic presses, the ingots are forged under immense pressure, improving the internal grain structure and mechanical properties. This forging stage is essential for eliminating voids and ensuring superior strength and durability. After forging, the steel blocks undergo heat treatment involving quenching and tempering cycles. These processes adjust hardness, relieve stresses, and enhance toughness. Precision-controlled furnaces and quench tanks ensure consistency throughout the entire block. The blocks are then machined using large-scale CNC equipment to achieve exact dimensions and surface finish required for aerospace tooling. Dimensional accuracy is critical at this stage to meet tight tolerances. Comprehensive inspection follows, including ultrasonic testing and magnetic particle examination to guarantee internal soundness and surface integrity. The final steel blocks are now ready for use in aerospace manufacturing machines, engineered for extreme strength, accuracy, and long service life in the most demanding environments. All that. The MC200 pipe and profile bending machine operates with 3 rollers arranged in a pyramid configuration. In the beginning, the operator positions the pipe between the lower and upper rollers. By adjusting the top roller downward using the hand wheel, pressure is applied to begin the bending process. The side rollers are powered and rotate in opposite directions, feeding the pipe through and creating a gradual curve. For tighter curves, the operator incrementally lowers the central roller between passes, allowing for greater deformation with each cycle. The machine is equipped with adjustable rollers to accommodate round pipes, square tubes, and profiles of various sizes. The control panel allows for forward and reverse rotation, ensuring precise shaping and easy removal of the workpiece. This cold bending process does not require heating the material and maintains the integrity of the pipe. The MC200 is commonly used for making circular frames, arches, and structural components in metal fabrication and construction industries. The M4 blacksmith tool is designed to twist metal bars into decorative basket shapes. The process begins by inserting the pre-cut metal rod into the machine's clamping system. Once secured, the operator activates the machine. Using motorized rotation and controlled feed, the machine gradually twists the metal, forming a symmetrical spiral or basket-like shape. A heating torch may be applied beforehand to improve metal flexibility and reduce stress during twisting. After the twisting cycle completes, the operator releases the clamps and removes the finished workpiece. The result is a uniform, decorative twisted basket, commonly used in gates, railings, and ornamental furniture. This tool significantly increases efficiency, consistency, and safety in blacksmith and metalworking operations. SMG Group's advanced galvanizing line features precision-controlled zinc coating with automated air knife systems, ensuring uniform thickness. Integrated PLC and HMI interfaces enable real-time process adjustments. With energy-efficient furnaces and inline defect detection, the line meets stringent standards for automotive and construction steel, delivering high durability and corrosion resistance with optimized production efficiency. Converter steelmaking utilizes molten iron, scrap steel, and ferroalloys, leveraging internal heat and exothermic reactions rather than external energy. Conducted in a refractory line converter, high-purity oxygen is blown in to oxidize and remove impurities like carbon, silicon, and sulfur. The result is low-carbon steel, efficiently refined at high temperatures. The casting of a new bell for Inverness Cathedral is a detailed and traditional process. It begins with designing the bell's profile and tonal characteristics. Craftsmen create a bell-shaped core from bricks and clay, followed by a wax or false bell layer that forms the exact shape and decorations. Over this, they build the outer mold, called the cope. Once the mold dries and hardens, it is heated to remove the wax, leaving a cavity between the core and cope. Molten bronze, an alloy of copper and tin, is then poured into this cavity. After cooling for several days, the mold is broken to reveal the rough bell. The bell is then cleaned, tuned by carefully removing material from the inside, and fitted with a clapper. Decorative inscriptions or patterns may be added. Finally, the finished bell is delivered and installed at the cathedral, ready to ring for generations to come, continuing a centuries-old tradition of craftsmanship and spiritual resonance. The T-profile forming machine begins by feeding a steel strip into the machine. The strip passes through several forming stations where gradually shaped rollers bend it into the desired T-profile. Each station incrementally changes the shape, ensuring precision and consistency. As the strip advances, it takes on the vertical web and horizontal flange structure characteristic of a T-profile. Once fully formed, the profile is cut to the desired length by a flying saw or cutter, synchronized with the line speed. The finished T-sections are then collected and stacked for further processing or shipment. The process is fully automated, ensuring high production efficiency, accuracy, and minimal material waste. Molten metal is poured into a horizontal mold, gradually solidifies, then continuously withdrawn, cooled, and cut into lengths for further processing. The brass production process at the Saint-Just-des-Vernes factory involves melting copper and zinc in a furnace, then casting the molten alloy into molds. After cooling, the solidified brass is removed and subjected to rolling, cutting, and polishing to achieve the desired shape and finish. The process involves precise cutting of thick steel plates, followed by hydraulic pressing to achieve the curved shape. Skilled welding joins multiple segments, ensuring strength and accuracy. Grinding and alignment are performed to refine the structure. Final inspection confirms the integrity of the 3,400 mm by 35 mm steel locomotive head before assembly. The 5-axis rolling machine forms cylindrical and conical tubes by precisely positioning rollers. The metal sheet is fed, aligned, and gradually bent by synchronized roller movements. The advanced control ensures accurate shaping for various diameters and taper angles. At John Taylor Bell Foundry, bell retuning begins by securely mounting the bell on a rotating lathe. Skilled craftsmen carefully remove small amounts of metal from the inner surface to adjust pitch and tone. Using precision tools and electronic tuners, they ensure each bell produces harmonious sounds, preserving musical accuracy and historical integrity. A 20 mm thick steel plate is positioned on a hydraulic press. Using a top die and a curved bottom support, the press gradually bends the plate into a smooth arc. This cold forming method allows precise bending of thick metal without applying heat. The cable stripping process begins by selecting wires ranging from 1.5 square millimeters to 6 square millimeters. Each wire is inserted into the appropriate slot of the stripping machine. Once activated, the machine precisely cuts the insulation without damaging the conductor. The operator then pulls the wire slightly to remove the insulation. This quick and efficient process ensures clean, consistent results, making it ideal for preparing electrical wires for further use. Brass turnings are fed into the shredder, where dual shafts grab, shear, and break them down into smaller, uniform, free-flowing pieces for recycling. First, artisans shape a mold using clay, sand, and wax to form the bell's detailed design. Once dried and hardened, molten bronze, an alloy of copper and tin, is poured into the mold. After cooling for several days, the mold is broken open to reveal the rough bell. The bell is then carefully cleaned, tuned, and polished by hand. Each bell is unique, reflecting centuries-old craftsmanship passed down through generations. The advanced manufacturing process of MTE's high-precision milling and drilling machines. The process begins with the careful design and engineering of each component using modern CAD software. Large cast iron structures, essential for machine stability, are machined to tight tolerances. The machining of these structural parts is carried out using large CNC machines, ensuring high accuracy and surface quality. Precision grinding and hand finishing are employed to guarantee alignment and parallelism. Key components such as spindles, rams, and rotary tables are assembled with attention to detail and quality control. After mechanical assembly, electrical systems and software are integrated to provide full 5-axis functionality and user-friendly control. Rigorous quality checks, including laser calibration and test runs, are conducted to verify the machine's performance. Finally, the machines are painted, labeled, and prepared for shipment. MTE's commitment to quality, innovation, and precision is reflected in every step of this process, resulting in reliable machines used in industries worldwide. The Orion Valves PAMA large-sized boring and milling machine is engineered for precision machining of sizable industrial components. The process begins by securely mounting the large valve body onto the machine's work table. The operator then programs the machine to execute specific boring and milling operations. The machine spindle, equipped with appropriate cutting tools, performs precise boring to create accurate holes, followed by milling to achieve the desired surface finish and dimensions. Throughout the process, the machine ensures high accuracy and repeatability, essential for producing components that meet stringent industrial standards. This integrated approach streamlines production, reduces manual intervention, and enhances overall efficiency in manufacturing large-scale valve components. The handmade water container is crafted from a flat metal sheet. First, the craftsman marks and cuts a circular piece of sheet metal. The disc is then placed on a spinning lathe. Using various handheld tools, the worker gradually shapes the spinning metal into a cylindrical form. After forming the main body, the base is created separately and welded to the cylinder. The top part is trimmed and smoothed for a neat finish. Next, the spout is formed and welded to the body. The handle is also made and attached by welding. After all components are assembled, the joints are polished. Finally, the entire container is cleaned and checked for leaks. This process requires skillful handwork, attention to detail, and precision to ensure the container is functional and aesthetically pleasing. The SMX 2100 is a high-precision, multitasking turning center designed for complex machining. Its workflow begins with securing the workpiece in the chuck. The machine then performs turning operations using the main spindle, followed by milling and drilling with the B-axis head. The sub-spindle enables simultaneous machining on both ends of the part. Advanced automation and synchronized tool changes enhance efficiency and accuracy, making it ideal for producing intricate components in a single setup. The silver cup is crafted through a metal spinning process. A flat silver disc is mounted on a lathe and spun at high speed. Using a forming tool, the artisan applies pressure, shaping the metal over a mandrel to achieve the desired cup form. This technique allows for seamless, symmetrical designs, combining precision with traditional craftsmanship. The operator begins by placing a metal bar into the feeding position of the machine. The bar is clamped securely using a set of hydraulic jaws. The operator then selects the pre-programmed forging sequence and activates the start cycle. The forming tool, mounted on the ram, moves horizontally toward the workpiece. The bar rotates slowly as the ram applies high pressure to deform the material against the die. This pressure forms the desired shape on the bar end without heating. During this process, the machine controls the speed and pressure to maintain uniformity in the forming operation. After the first forming stroke, the ram retracts to its initial position. The machine then performs a second stroke, depending on the complexity of the shape. Between strokes, the bar may be repositioned or indexed to ensure complete shaping. The movement is fully automated and synchronized with the ram's motion. Once the forging is complete, the clamping system releases the bar. The operator removes the finished piece and loads the next raw bar. The machine resets automatically for the next cycle. Throughout the entire operation, sensors monitor the position and pressure to ensure consistency and precision. Each cycle follows a set pattern: clamping, forming strokes, retracting, and unloading. The machine operates smoothly, with minimal vibration, and all movements, clamping, forming, releasing, are hydraulic and controlled through a touchscreen interface. The forming tools can be changed quickly to accommodate different shapes. The production process of HBAM spiral tubes consists of three main steps. First, steel bars are optionally patterned using a HBAM rolling machine. Next, the bars are heated to 800 to 1000 degrees Celsius to soften the material and prepare for forming. Finally, the heated steel is placed into a HBAM bending machine to create spiral shapes, scrolls, S-curves, or other decorative designs based on the intended pattern. The production process of a paint roller with a plastic handle begins with forming the metal frame L-shaped from steel wire, typically 3 to 8 millimeters in diameter. The wire is straightened and cut to standard lengths, then bent into an L shape. The ends of the frame are chamfered and threaded to allow secure assembly with the plastic handle. Next, the handle is manufactured using an injection molding machine. Plastic pellets are fed into the machine, melted, and injected into a mold designed with grooves and slots for better grip and comfort. Once cooled, the handle is removed and inspected for quality. Assembly follows. The metal frame is inserted into the plastic handle using an automated system. Pneumatic pressure ensures a tight, secure fit. Finally, the roller tube is attached to the opposite end of the frame, allowing smooth rotation without jamming, completing the paint roller assembly. The 4HI brass rolling mill operates by passing a brass strip through a set of 4 rolls, 2 smaller work rolls, and 2 larger backup rolls. Initially, the brass coil is uncoiled and fed into the mill. As the strip enters the rolling zone, the work rolls apply pressure to reduce its thickness, while the backup rolls provide support to prevent deflection. This configuration ensures uniform thickness and surface finish. Throughout the process, the strip is continuously guided and tensioned to maintain alignment. After achieving the desired thickness, the rolled brass is recoiled for further processing or shipment. This method enhances material properties and dimensional accuracy, making it suitable for various industrial applications. An advanced turning milling component made from C45 steel is precisely machined on the Okuma Multis CNC Turning Center. The process begins with clamping the steel workpiece securely in the chuck. High-speed turning operations shape the outer contours, followed by milling to create complex geometries, including holes and slots. The Multis BII's multi-axis capabilities allow for seamless transitions between operations, ensuring high accuracy and surface quality. Thanks to the machine's automatic tool changer and synchronized movements, setup time is reduced and production efficiency is enhanced. This integration of turning and milling on a single machine minimizes repositioning, making it ideal for producing complex steel parts in a single setup. Working process of the cable stripping machine. Model WL620. The WL620 pneumatic cable stripping machine is designed for stripping large cables up to E50 millimeters. Operated by air pressure, 5 to 6 kilograms per square centimeter, it uses a 100 millimeter cylinder to drive blades that precisely cut insulation without harming internal wires. With a stripping stroke of 200 millimeters and maximum stripping length of 600 millimeters, the cable is fed into the inlet, cut by rotating blades, and exits cleanly stripped. Powered by AC 110 volts / 220 V, this machine ensures high efficiency and accurate stripping. The Midas 300S dry copper cable separator processes cables through shredding, granulating, and vibrating separation. Initially, cables are shredded into smaller pieces. These pieces are then granulated into finer particles. Finally, a vibrating separator separates copper from plastic insulation, yielding clean, recyclable copper and plastic materials. A copper disc is spun on a lathe, shaped over a mandrel with tools, gradually forming a symmetrical vase through applied pressure. This technique involves mounting a flat copper disc onto a lathe, where it's rotated at high speeds.